let's get started. Let's move on through chapter 2. Okay, so section 2.2. So that's the limit of a function. We're going to have a look at the idea of a limit. How is that related? How is that similar? How is that different from computing values of functions, which is what we did all over this algebra courses, intermediate algebra, college algebra, pre-calculus, you name it. All right, and well, so we're going to introduce a new concept. Well, some of you may have taken a calculus class and you know something about it, so that's fine. But let's see. Let's brainstorm some ideas here. So, what comes to your mind when you hear the word limit? Any ideas? Limit. And don't even think of like mathematically functions, not yet, just the max value. Maximum value, right? So some sort of a maximum. And not just the maximum, we also could think of, the smallest as well, right? Like the minimum. All right, oops, I didn't come out very well. Minimum and maximum. All right, anything else besides like maximum or the minimum, any other ideas? Yes.
Like an end date, something that will not be crossed.
Okay, how about we call that a stopping point, right? Stopping point. That's how far we can get, right? At that point. Anything else? What other ideas?
Domain and range.
The rate of change?
Domain and range.
Oh, domain and range. Well, domain and range. Well, that's something we will take into account when computing the limit, but I mean, not even mathematically, just in general for the word limit. Well, I will do one more. How about restriction? All right? Restriction. Well, so let's have a look at this. Let's have a look at what we did in intermediate algebra, and let's put it together to come up with the concept of limit. How is that different? How is that very similar to? Well, so we're given a function f of x, which is, in this case, let's go with something simple. F of x equals to x plus 3. All right? So in this case, well, we're told that the values of x, well, in this case, the x's are the inputs, right? That's actually the domain. That's part of the domain of the function. And these ones are approaching to 4. And what are the values? The outputs approaching in this case. So we're going to approach to a specific value. Well, so number 1. This is what we did in intermediate algebra. F of 4. What does that f of 4 mean? What do we do when we see this notation?
You plug it in.
Plug in, replace, right? So whenever we see the letter x, replace. So that's 2 times 4, which is x plus 3 equals 11. All right? This is what we did. So the function is defined. That's what we say in intermediate algebra. The function f of x is defined for x equals to 4 and its value is 11. Okay, so that's how we interpreted these results back in algebra. But well, so let's see. These limits numerically are going to pretty much tell us what the concept of limit is. So in this case, well, we have this function f of x. Let's draw a number line. This number line will be all the numbers closer to 4. But well, we can approach the number 4 from two directions, either from the left or we can approach from the right. For example, values coming from the left, well, how about 1, 2, 3, 3.5, 3.9, 3.999, 3.99999, very closer and closer and closer, but without exactly touching that number of 5. So that's from the left. And let's label all this. From the left. Alright. From the right, well, let's list some values here. I don't know, so what do we have? 5, 6, 7. Okay, if we approach from the right, we can go 7, 6, 5, 4.5, 4.1, 4.01, 4.001, 4.00001, and eventually get to that value of x equals to 4. Well, so in this case, let's label this as from the right. And well, to avoid doing all this calculation, I have this table of values for you, so we don't have to do like last time we computed a few. And well, so in this case, well, f of evaluated at 2, the y value equals 7. So 2 times 2, which is 4, plus 3 equals 7. And then f of 3.6, 10.2, f of 3.9, 3.99, 3.999. And well, this value with these 3 dots apparently will be the number 4, and it makes sense because, well, look at the value from the right. That's 4. When observing the y values, well, suppose we didn't know that this was going to be f of 11. Well, that's a whole different concept. Even though the mechanics are treated in a very similar way, these are two totally different concepts. Well, 10.2, 10.8, 10.98, 10.998, 10.999998. Well, what would be the next integer? Possibly be 11. All right. Okay. Graphically, so we have the graph of y. Y equals to 2x plus 3. That's the graph right here. And well, let's observe the x's. From the left, we're approaching x. From the right, we're approaching left. So that is, we're going to approach x arbitrarily small from both directions. And well, the y value that we will be getting is, well, coincidentally with the value of f of 4, which in this case is 11. However, we need to be very careful with these two different concepts before. Number one, the way we write f of 4 equals to 11 has a special meaning, has one meaning. Which point do we stand on when x equals to 4? And well, that point is 4, 11. In other words, is a function defined? Yes. That is, can I stand on that point? Yes. Now, writing this in the language of limit, well, in this particular case, we got that the limit is exactly the value of the function. However, the way we are going to denote this is limit of function f of x as x approaches 4, just plain vanilla 4. Of course, we're going to look at limits from the side, from the left, or from the right. But in this case, well, let's just keep it simple, equals 11. And in this case, the way we read limit of f of x as, or the limit as x approaches 4 is 11. Okay, what's the difference between the limit and the function? Okay, so the function again tell us the answer to the question. Can we stand at that point? If it is defined, well, yes, f of 4 equals 11. That means you're walking 4 units in the x direction and then 11 units in the y direction, and you're going to be standing at that particular point. Now, what about the limit? So, the limit, however, tells us the following idea. What is the value f of x approaches to when x approaches 4. All right, in this case, one thing, the function f of x is, can we stand there, yes or no, and that's depending on whether the function is defined or not defined at a value. The limit, on the other hand, is how close can we get to that value. And the problem with this limit is because we can have functions for which, number one, the function may not be defined at that value we're approaching to. However, we can approximate and get as close as possible, but without actually getting to the value of the function. Well, let's look first of all at the definition, then I'll give you the 3 different cases in which this approximation versus can we stand there, can we not stand there. Well, let's see. The formal definition. So we have some function f of x defined when x is near to some number a, which is the value that x is approaching to. This means in this case that f of x is defined on an open interval containing that value a, and in this case it is possible that that function is not defined by a itself. That doesn't matter because the question here is not anymore can we stand at that point. No, the question is how close do we get? How close do we get? Alright? So we say the limit of f of x as x approaches a equals L in a similar way as in the example. Well, this one is in general with symbols. We already did it before with one numerical example. Alright? So, well, 3 different case scenarios. And let's observe these graphs right here. Okay? So, in this case, let's analyze for these 3 functions, whether number 1, f of x is defined and whether the limit exists. So at the value of x equals to a. So let's label this our x equals to a, and this is L. X equals to a, L. X equals to a, and well. So number 1. Here we have the first case in which the value of x that we're approaching to, which is just a, any value, doesn't matter what value is it. So, number 1, the limit exists, and also limit exists and f of x exists at a, more specifically at x equals a, and f of x is defined at x equals to a. So we have the case in which we have a really nice function, continuous function. Both the function is defined and the limit at that value of x also exists. Alright, let's see this weird case right here. Notice we have this open bubble, but we have in this case this point in the middle of nowhere. That's fine. You might have seen this type of functions where you have like a piecewise defined function, whatever equation is, except at some value of x, and well, that point declare on a separate equation. Well, so without going through those details, number one, so to evaluate, well, let's look at the limit. Let's see if the limit exists. Well, in this case, the limit exists because, well, we can approach the same value. Notice I'm approaching this open bubble from the left, but I can also approach this open bubble from the right. Alright, so in this case, I'm getting as close as possible without getting into the hole, because, well, I get stuck in the hole and, well, goodbye, right? But that's why we're not looking at whether I can stand at that point. Alright, so we're looking at the limit, and let's call it L. So limit exists at x equals to a, and the limit is this y value, which we call L. Whatever that value is. We're going to look at some numerical examples soon. Right now I'm just giving you the bigger picture. How are we going to approach this? And also, f of x is defined at x equals a. However, check this out, check the difference. In the previous case scenario, we got the limit existing at a, and both the limit and the value of the function being exactly the same value. However, in this case, the limit is one value, however, the function is defined somewhere else. In this case, can we stand at this point where we have a hole? Not really, right? But can we stand at this point? Yes, so in this case, f of x is defined at x equals to a. However, in this case, limit of f of x is not equal to f of a. All right, these are not the same quantities. All right, and let's look at the third case scenario. So the third case scenario, we have this graph representing any arbitrary function, and yes, we still have this open bubble here. But the question here is, number one, does the limit exist? Okay, let's approach from the left and let's approach from the right. In this case, because we are seemingly getting to the same value regardless of the direction that we get to this hole, well, the limit exists. Yes, we cannot touch that point. We cannot stand on that point. We're only approaching. That's why we make the difference between a limit and evaluating a function, because it's how, for example, this is a function, the hole starts right here. I can get as close as possible, but can I go beyond the table? Not anymore. So this is the point I can get as closest to that hole, or asymptote. Later on we're going to see this in terms of asymptotes. Jump discontinuities, you'll see. Let's look at this case. Well, the limit exists, but what about f of x? Is f of x defined? Why is f of x not defined in this third case scenario? In other words, okay, think of, can we stand at that point when x equals a? Do we have a point to stand? No, f of x is not defined. Alright, f of x is not defined. Because in this case, well, even though we had an open bubble right here, For the second case scenario, we got the limit to exist, right? We could get as close as possible. But in this case, as far as the function can we stand, well, we have somewhere to stand at this point. However, in this case, we have nowhere to stand. That means f of x is not defined. It would be undefined, but the limit yet still exists. All right? Okay, so that's briefly, like the bigger picture of how we are going to treat these ideas. And let's have a look at one numerical example. Okay, so let's see. We have the function f of x equals x squared minus 1 over x minus 1. So the question is 1 in the domain of f of x? Yes or no? No, we say no. Why not? We get undefined, right? So for example, let's see. If f of x, f of 1 equals 1 squared minus 1 over 1 minus 1, that's essentially 0 over 0. Okay, the 0 in the numerator, that's fine because 0 times any number is 0. However, the problem is when the 0 is in the denominator, and unfortunately we cannot divide by 0 yet.
If you make it x minus 1, x plus 1, the numerator, you can cancel the x minus 1.
That's where we're going. That's where we're going. All right. So here, okay, is 1 in the domain? No. And as a full sentence, and to stick with these definitions between or rather to distinguish between these definitions between limit and function, no, we say no, f of 1 is not defined. All right, it's not defined. Okay. Now the question is, what happens as x approaches 1 but it's not equal to 1? Well, so we're going to have a look at these tables right here. Okay. And I'm giving you these tables of values rather than having to plug in different values for x and take the entire lecture getting these values. So for example, this function f of x equals to x squared minus 1 over x minus 1 evaluated at 2. Well, that's a 2 squared, which is 4, minus 1, that's 3, and 2 minus 1, which is 1, that's 3 over 1, which is 3. All right, let's verify this one. That's correct. Well, the remaining values are fine. So we want to find the limit. That is, the limit ultimately is what is the y value that the function is apparently taken. Well, we're going to look at a pattern here from the left and from the right. From the left, from the right. Well, f of 2, which is equals to 3. All right, and then reduces to 2.5, 2.1, 2.01, 2.001, 2.00001. Well, what's the apparent value of y being hit in the long run? 2. Let's look at the limit from the left. Well, if we evaluate the function at 0, so f of 0, 0 squared minus 1 over 0 minus 1, that's a negative 1 over negative 1, that's positive 1. Should be the same for these different values of x. But it doesn't matter. What I want you to see here is, in a similar way as approaching from the right, what is the apparent value of y being hit from the left? 2 as well? 2. Okay. Well, and let's see. How come we are still approaching some value even though f of 2, f of 1 is not defined? Again, because these are two totally different concepts, even though the mechanics and later on when we start computing limits, algebra, yes, we are going to substitute a value and boom, 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 get that 0 over 0. You get a number, cool, we're done, we got it, that's the answer. Otherwise, 0 over 0. Do some algebra, you get anything weird, well, let's look at the graph. We're going to look at various techniques to compute limits, various approaches. But again, one thing to keep in mind is that limits Evaluating limits, it's not just evaluating at the value of x, because all we would be doing there is just evaluating a function. And again, these are two totally different concepts. Function is, we stand at that point. Limit is how close can we get as x approaches some value. Well, and let's see. So what happens? So f of x approaches 2. And well, taking the comment by one of our classmates here, well, he mentioned, how about we simplify this function, take this as a difference of squared? Yes, why not? So f of x plus 1, x minus 1 over x minus 1. We can reduce this. This is f of x equals to x plus 1. And in this case, we can safely plug in f of 1. We can evaluate f of 1. However, the problem with this is that we had 0 over 0 indeterminate form coming from the original function. Okay. Number one. Just before, I'm going to show you something on the graphing calculator. However, what kind of function is this? Linear. All right? Okay. Let me go to the graphing calculator. I'm going to graph the original function, not the reduced function. Okay, so I'm gonna go y. Oh no, I'm in parametric mode. Enter. Y. Clear. Okay, so what did we have? Open parentheses, x squared minus 1, close parentheses, divide by, open, x minus 1. Okay, so let's graph this weird function. Okay, x squared minus 1 over x minus 1. Graph. Wait, that looks like a linear function, isn't it? Isn't this linear function the same linear function that we got when we reduced this function? Yes. However, there's an issue here, and this is where you don't want to rely on graphing calculators all the time, because yes, graphing calculators are very, very smart devices. That is true. However, they're not that smart, unfortunately, because, well, from the theory of functions back in pre-calculus, when we discussed, all the different discontinuities. So one of them that we discussed in the theory of rational functions, asymptotes. Remember those asymptotes, values of x that we cannot just evaluate those functions at, but we can just get as close as we can. All right. Then we also have these holes as well, and those holes were produced when factors get cancelled. All right, and that hole is at the value of x that gets cancelled, in this case the function, the value for which it's not defined. So really what I'm trying to say here is the following. Yes, we are still going to get the graph of a linear function. However, well, let me do it here, I need more space. However, okay, the f of x equals x plus 1, that's go 1, that's the y-intercept, and rise over run 1, and well, but again, we said that the function is not defined at x equals 1. Because the function is not defined at x equals 1, this means that we should have a hole in here. Alright? And unfortunately, your graphing calculator is never going to show those holes. In fact, it's not even going to show vertical asymptotes either. It's going to show some weird vertical lines that are not the dashed lines that we're used to when looking at this kind of vertical asymptotes. So yes, now coming back, this will relate to one of the cases here, to the third case scenario, in which yes, the limit exists. All right. However, is a function defined? Don't we have the same case here? F is not defined at 1. However, the limit exists. So what we did by simplifying the function, the expression right here, to obtain a simpler function for which we can actually evaluate, because we're really not evaluating, we are using these algebraic techniques as a mean to compute the limit, but not the value, because it's undefined. We have an open circle in this case. All right. Well, before looking into this, I was talking about limits from the left and limits from the right. That is what we call one-side limits. And well, what's the notation? Well, we already looked a little bit at notation of limits. Limit of f of x as x approaches a equals L. However, we are going to have this superscript the values of a x is approaching to. When you see the negative symbol, the negative sign, that means we are approaching from the left. But when you see the plus symbol, the plus sign, that means we're approaching from the right. And well, here's a formal definition, a lot of words, blah blah blah. We say the left hand limit f of x as x approaches a, or the limit f of x as x approaches a from the left, it's equal to the limit by making those values arbitrarily close. All right? And again, it is possible that the function is defined or not defined. It doesn't matter if the function is defined or not defined, because that's not what we care anymore. We care about the limit. Where are we approaching to? How close can I get to that value without actually hitting that value? That doesn't matter anymore. Well, so the same definition for the right-hand limit, just to replace the word left with the word right. The thing here is, it's very important, this conclusion right here. If both limits, that is the limit from the left and the limit from the right, both approach the same y value, well, the limit exists. However, if from the left you approach one value and from the right you approach another value, well, you're getting to different values from different directions, so the limit does not exist in that case. And well, I know this section, it's been already too many words, too many symbols, too many concepts. Let's see all this in action in a different way. So we have this graph right here. So we have the graph of h of x, and it doesn't matter what's the rule, if it's x cubed plus 1, some parabola, doesn't matter. We got the graph, which is what matters. Number 1, what's h of negative 2 from the graph? Anyone? 2. Okay, so when x equals negative 2, be careful. Because number 1, we have this open bubble in the middle of nowhere, but we also have this open bubble. Okay, the question is, h of negative 2 tells us about, can we stand at that point? So we are going to we're going to list the value for which we can stand on. In this case, that's going to be indeed 2. All right. Now let's see, what's the limit as h of h as x approaches 4? Okay, number 1. So in this case, I need to verify a couple of things. So I'm going to use the side limit. So when approaching from the left, so limit h of x approaching from the left and limit x approaching 4 from the right. Okay, let me approach from the left. What's the y value apparently being hit when I approach from the left? 2. What's the limit apparently, or what's the y value being hit when I approach from the right otherwise? It's the same limit, it's the same value, right? So in this case, when we get the same limit from both sides, that means, limit from the left, limit from the right, limit plain vanilla 4, it's going to be also 2 because these two limits are coincident. If for whatever reason we get to different values, as we will see in another example, well, we have problems in there. So, okay, what's h of 4? Can we stand at that point where x equals to 4? No. What happens if we stand there? Well, we get sucked into the black hole. Goodbye. So what does that mean in terms of the function? Undefined. Yes, undefined. All right. Okay, let's look at side limits. Okay, limit 8 of h of x as x approaches negative 2 from the left. Okay, negative 2 from the left. So what is the y value apparently being hit from the left? 1. What about from the right? 1 as well, because in this case now, limit from the left is 1, limit from the right is 1. Plain vanilla 2, because these two limits are the same. Okay, well, that limit is 1. All right. Limit h of x as x approaching 0 from the left. All right, so this time around, I'm going to approach 0 from the left. Okay. What is the y value apparently being hit? 3. Now, what about x approaching 0 from the right? 2. Oh, hold on. We are approaching two different places from either side. All right? I mean, so you can think of this. So, if you go from Freeway 5 towards the north, and then there's another car coming from LA. So you're converging to the same point in different directions, right? However, let's say the intersection between the 5 and the 8 to come to SDSU, okay? However, if there's a car coming from the south to the north from Freeway 15 and then one on the Freeway 5, are they approaching the same intersection? No, right? So in this case, what do we have? Well, number 1, this is 2, right? This is 2. In this case, because these two limits were different from either side, limit plain vanilla 0, we say DNE, the limit does not exist. The limit does not exist in this situation. We have to get to the same, we have to approach the same value from both directions so that we can say, oh, the limit, boom, is this. Except possibly whether the function is defined or undefined. Doesn't matter. Again, the concept of limit is approaching. The concept of a function is, can we send at that point? Well, so that's something different. Now, what is h of 0? Interesting, huh? 3, right? Yes, we have like a couple of choices to choose from. Well, but again, I mean, this is an open bubble, right? I mean, we cannot stand at that point, but we have this solid bubble to save us, so we can stand there, right? And that's when y equals to 3. And well, it's very important to have this down because, I mean, sometimes we say, oh, the function does not exist and the limit is undefined. No, these are reverse ideas again. Functions are defined or undefined, and limits do exist or do not exist. So try not to mix up the wordings here, all right? Are you guys following me here? Is this making sense so far? About how we treat limits? Well, so far we have limits from pictures. Okay, now what about infinite limits? I mean, on the limits that we discussed before, well, so we were looking at values approaching, well, maybe 5, maybe 3, you know, finite numbers. But of course, there's other kinds of limits. Limits approaching to infinity, blowing up to infinity, and yes, technically we should say D and E, because the limit does not exist, because it just floats up forever, it goes to infinity. But in this case, we can approach to different infinities or to the same infinity from either direction, and that's where it's important to, instead of saying D and E does not exist, we need to say it exists. Okay, so let's plug in some values of x. Okay, so to this function, to the function defined by f of x equals to 1 over x squared. Let's make a table of values. So we have the table of values, and in this case, f of 0.1, this is 1 over 0.1 quantity squared. But okay, without using a calculator, that's a 1 over 0.1, which is 1 over 10. That's 1/10. Square that number. That's 1 over 100, which is 100 when we flip the fraction. Okay, what do we have here? 100 in the negative. Oh, we'll look at the negative in a second. 0.01 is not going to be, well, it's going to be, I'm just going to give you the value, 1 times 10 to the 4th. Really doesn't matter the value. What I want you to see anyway is how is this number, well, what's going on here? We're going from 100 to 10 to the 4, and then to 10 to the 6, 10 to the 7, 10 to the 35. How big is this number going to? Where is this going to? Infinity. Alright? In this case, well, when we evaluate the same value but negative, it doesn't matter, because that negative is going to get squared and it's going to become positive. Well, so in this case, where are we going to? Also infinity. Alright guys, so at the beginning of the semester we did a review of the different parent graphs. So this is looking at the table of values and observe how the values increase big and big and big, eventually going to infinity. That means that we still have 5 minutes, guys. So that means, let's recall the graph of f of x equals 1 over x squared, and we'll look at the graph being this, right? So essentially, we're looking at the limit as x approaching 0. Okay, we want to know the limit plain vanilla 0, not from the left, not just from the left, not just from the right, but of course in this case we need to look at the limits from both sides. Okay, so the limit from the right, limit f of x, x approaches 0 from the right, and limit f of x as x approaches 0 from the left. Okay, let's approach from the right. When we approach from the right, what is this graph? Where is this graph going to? Infinity. All right. What about from the left? Infinity. Are we going to the same value? Yes. So this is infinity. Okay. In contrast, well, I don't want to move on to the next. Okay, let me just give you the what if here. Let me give you the what if. What about limit? What about limit f of limit of limit of 1 over x instead of 1 over x squared as x approaches 0? Well, let's look at the graph of, instead of doing the table, let's look at the graph of, and from the parent functions we have these two curves pointing in different directions. So in this case, to be able to compute this limit right here, we would need to look at the limit from the side. Limit x approaching 0 from the left, limit x approaching 0 from the right. Alright, okay, let's analyze the limit from the left. Where is this approaching from the left? Where is it going to this time? Negative infinity, alright? Negative infinity. And what about from the right? Where is it going to this time? Positive infinity. Okay, let's observe each individual limit. So, what about plain vanilla 0? Are the two side limits the same? No. So what's this limit then? Huh? Not undefined. That's for functions. We're not evaluating functions. We're finding limits. What was that? Does not exist. D and E. Alright, so that's the difference. We're going to do a bit more of this